everybody, my name is Pixel Rain or Mark as you may know me, and today we'll be continuing our tutorial on setting up RayMarch based voxels. Today we'll be adding a fairly simple editor system that will allow you to place cells manually, delete cells, all that good stuff. It's going to be a little haphazard because it was written with the RayMarching material already set up, but enough of that. Let's go ahead and get into it. We're going to start in our voxel object script. And the key thing we're doing here is we're going to be adding another struct down here below the serialized node that is called a GPU node, because this is what gets passed to the RayMarch shader for rendering when we get to that, which will be the next video. It's a fairly simple struct here. It's got a vector3 position, half size, which is the half size of the bounds, the child index, which is for the linear array, which we'll go over in a minute, and then the voxel data itself, which is in fact an integer because you can't pass shorts or bytes into shaders, so we have to go to an integer, which sucks because it's just more memory utilization, but that's fine. And there's also a simple helper function here for contains, and that calculates the AABB of the node itself using the position and the half size. And with that out of the way, we'll go ahead and scroll up here just past the clear functions, and we're going to be adding two new functions to this. This is a recursive set of functions, so this is the primary function. If the root is null, we return out early with a empty array. If the root isn't null and we're continuing normally, we initialize a new list of GPU nodes and we add the root node to it first. So that starts with the root's position, the bound size .x divided by 2. Could just use extents, that would also function. This parameter here is the child index, so the first child of this octant is going to be 1 because obviously index 0 is the root. And then the voxel data is set to -1, which is just how we can return out early when we get to the draw stages. Then we call flatten node GPU. I know, great names. You can name them whatever you would like, but this is the recursive function that actually fills up our linear node list, and we start from node 0. This is pretty simple in the way it works. If the node is null, we return -1, and this returns an integer for indexing sake, as you'll see here shortly. If the node has children, we're going to set up our child index based on the lists index, or the lists count. And then we'll iterate over all 8 of our children. We will add placeholder nodes into the list at the location based off this derived count. This is pretty standard. It's just setting everything to null unless there's a voxel. Then we set the voxel data to the actual data held within that voxel. And if you don't remember, data is the accessor directly to the voxel field within our voxel struct. Then we go ahead and reduce our half size by 2 to continue shrinking down within the octants. And then we add that placeholder to the list. Next up, we reiterate through the children, and this one is set up so that when it runs flatten node GPU in that recursion call, it returns the new child index, which happens down here, after creating more children as necessary, because if there's no children, obviously we're not going to have a child index, so it'll be -1. So what we do here is we get a copy of the current node we're at from linear nodes. We set the child index based on the return value from flatten node GPU's recursion. We pass in the required variables, and then we reassign that copy of child node back into the list at the correct index. And then because that's assigning the child node, we also want to update our actual node that we're currently iterating on based on that node index, and just set the first child index to that and return out. And if there's no children, we want to return -1 because the whole point of this is to set up a easily parsed linear array. Moving on, we will bounce over to the voxel container. This is going to have some stuff that is absolutely not getting used until we set up the RayMarching, but it would be easier to just set up now. So the first thing we're doing is we're adding a private runtime object for a new voxel object. That'll be so when you're running in game, you can make changes to the voxel object without messing up your actual serialized object. Then we're going to add all of the parameters that are used for actually ray marching. Most of this isn't used yet, but we're going to do a full initialization as part of this update. So the next one should be right into the actual ray marching code. So from the top, we have our ray marching material that you'll assign. The scene light, we're only working with a single light for the moment. We will probably add more in the future. We have a Boolean for dynamic, and that's going to be used to control whether the voxel container should simulate physics on a break. We have 2 compute buffers, one for the linearized octree and one for the voxel colors. Then we have a private array for the GPU nodes that are generated when we compute the buffers, and some simple Booleans to keep track of our state. Moving down to the awake function, we're going to be adding a simple if application is playing, initialize buffers to make sure that the voxel object is initialized and the shader will be able to actually draw. Then we're going to be adding a rather large chunk of code here down where we had destroy buffers because we're actually implementing the buffer functionality right now. So from the top down, we have initialize buffers with a force variable just to prevent us from remaking compute buffers unless it's absolutely necessary. So we just early out if we've already initialized and force is false. Then the next thing we're going to do during this initialization is we're going to instantiate a copy of the voxel object into that runtime object reference. And then during initialization, we're also going to just keep tabs of is playing because some of these calls happen asynchronously later on, and you can't actually access application.isPlaying when you're not on the main thread in Unity for whatever reason. Next up, we assign our linear array to that voxel object flattened for GPU function we went over a few minutes ago. Then we release the buffers if they're already set, which is what this null indicator is for. And then if our node's length is 0, so there's no nodes, which really should be less than or equal to 1 now that I'm thinking about it, but it's fine. We're mostly trying to catch if the array is null here. Then we want to early out. After that, we initialize our octree buffer with the count of nodes.length, a stride of 24, and a type of default. And then we set the data in there to our nodes array. Next, we set up the color buffer, which is done similarly with the colors set up in our voxel settings, a stride of 16 for RGBA, and a default type here as well. And then we go ahead and set the data to what is inside our voxel colors array. Then we get down into if our ray marching material is not null, then we check if the ray marching material contains clone. If it doesn't, we want to instantiate a new one, essentially cloning whatever material you're using so that you can have multiple buffers being set and it's not trying to share the same material. And then we assign the buffers based on that new material we have set up, and we assign that material back to the mesh renderer itself. And next up, we're going to start getting into how the ray marching shader is actually going to work, because this is essentially just a CPU derivative of how the ray intersection calculations work. I'm not going to get too deep into the math here, mostly because I probably cheated a little bit and used ChatGPT for this section because I'm bad at math, but that's fine. I'm not here to gloat about being a great programmer. So the first thing we do is calculate the inverse direction of the ray that we're looking at. So in this case, it'll be screen point from the camera center or camera origin, sorry. And that's done just by dividing 1 divided by ray direction. And then for the next chunk of this, we're essentially just going to be calculating where the ray is expected to intersect, including the distance if the ray is originating from outside of the bounding box. As you can see here, if the ray originates inside the box or the ray doesn't have an intersection, we early out, although with different returns, because if we're inside the box, then we want to return true. That's the entire check here, is whether the ray intersects the box. Moving down to the actual call that's used in the editor script, we have a function called array_intersect that takes in a array. We have some safety early outs here, nodes length equals 0 or node 0. Our root has no children, then we want to just return a failure to get a array intersection. And then this is the actual code that handles rendering the octants when we get into the shader itself. We set a default candidate count of 1 representing the root node here. We have our default boolean hit equals false, and then we have our initializations for hit normal and hit center, which is the center of the node we hit. Then we set up a array of 16 candidates, which we'll cover the struct here in a minute when we get through this section. It's a fairly simple struct. I believe it just holds the node index within the array and the distance to the array origin. Yeah, right here. So our initial root is set up with 0 and 0. It's the closest thing essentially at this point. And then we work through the candidates, trying to decrease our number until we've found the closest box to our array direction. And fortunately, some of the comments in here are pretty self-explanatory. In this case, we find the closest candidate via just a raw comparison of distance here. And then if whatever candidate we're looking at is closer than our current closest candidate, so in this case root, we update the candidate index. Then we get a copy of that closest candidate and we do a little shuffling around within the array here and decrement the candidate count. Next up, we're going to start getting into the actual array intersection testing. First thing we do is we check if there is any voxel data here. If not, we don't really care. It's an empty cell, so we don't count it. This is our check for if we're hitting a leaf cell with voxel data. Otherwise, it's obviously not going to count here, and we don't really care if we're just hitting air. So this takes in the array origin, the distance that we've calculated further down here, and multiplies our array direction by that distance to get the edge where we're hitting. Then we set up all of our return values here. So the hit center is the current node's center. The hit normal is the object position plus the node position minus the current position, and that's normalized, and that'll return what face we're hitting on the cell. And if we haven't recursed into a leaf here, we're going to go ahead and iterate over all of the children. We're going to do an early out where if the child index plus I is greater than or equal to the length of our nodes array, or the child index plus I is less than 0, and that's going to be if our child index is -1. If our child index is -1, we want to go ahead and just continue through this for loop. Next up, we grab a copy of whatever node we're currently looking at. We create a new instance of vbounds, which we'll also go over here in a little bit. It's just a cheap implementation of a bounding box set up from our child node. Now, if we're looking at a leaf with no data, we want to go ahead and continue. That means there's no children, but there's also no voxel data that we care about. Then we go ahead and run our array box intersection, and this is where we calculate the actual distance that was being used above here. And once we have our distance to child calculated, we go ahead and initialize a new candidate and add it to our candidate nodes. And then for completeness, we return out based on our hit normal, hit center, and vector 0. At this point, that's going to also be default. The only time we return any data is up here on this voxel data check. Moving down, we have our destroy buffers, which is the last chunk of code I added. And in this, we're just disposing of our buffers. If they're not null, then we're setting them to null to clear out any references that we had, and we're setting it as initialized to false. The last thing we're going to do in this class is we're going to add our candidate struct and our vbound struct. As you can see, the candidate struct is super simple. It is just a node index integer and a float distance. The vbounds is also fairly straightforward. It is a float 3 min, max, and center. It has that same contains function that was in our GPU node essentially, but this has the actual min and max values outside as variables, and those are initialized when you create the vbounds itself. And the vbounds can be created via either passing in a node itself or in the world position, or with the center and size. It's essentially the same thing either way. Then you get the half size of the node. You add the world position, which is going to be, the object's world position to the node position, and you calculate the min and max based off of the half size, and then you assign everything back up. So that's going to wrap up our changes in the voxel container. Now we're going to go back into Unity, and we're going to go ahead and add a new folder called editor under our scripts. And we're going to create a new script called Voxel Editor. And just like before, I'm going to just paste in all of the code for this, and we'll go through it from top to bottom. So starting with the new stuff, this is a custom editor for our voxel container. We have several values that are used with the actual editing here. Like, these are all properties of a voxel that's being placed. We have a reference to our voxel setting, a default window position for our little in-editor window that we use. We have the 3 edit modes right now: add, remove, replace, and we have a variable to keep track of which mode we're in. On enable, so when you click on a voxel container, it's going to go ahead and load up the voxel settings. It's going to assign our voxel container to our target from the editor, and then we'll early out if there is no voxel object, which again is that serialized object that just sits in the voxel container, since the voxel container is just a glorified renderer at this point. And then we'll go ahead and initialize the buffers on the voxel container. That'll set up the material and all of that good stuff. So when you click onto a voxel container, if it's not rendering anything, it'll pop up once we get the shader set up. Next up, we have our draw settings window. This is called from our on-scene GUI, but we're gonna just go top down here. As always, we get our voxel container based off our target, and then we start by drawing a label that just says voxel settings, and then this is going to be a toolbar. Then we're going to draw a toolbar, which is going to be like a little options field based on the edit modes. And then we also are going to use a couple change checks here, because when you update the selected voxel ID, you want to go ahead and update the color selector to match that. So that's all this is really doing. We're updating the voxel ID based on that, and then we're making sure we're still in range of our voxel colors array. And then following up on that same section of changing, we also update the actual color editor that we use here. So we do another change check. This is going to have a pop-up confirming the color change, because updating the color will affect all voxels with that ID. And then we update the actual voxel settings voxel color to our new color, and we reinitialize our buffers. And then we have a few other fields for our additions. These are all the voxel properties again. And then we make the entire window draggable. Getting into on scene GUI, the last little chunk of code here, we, as always, get our target. We check if the voxel object, scriptable object, we check if the voxel object is null and early out if it is. Then we check if the root within that object is null. If it is, we initialize with some default parameters here. Then we draw our floating toolbar by calling GUI layout window against that draw settings window that we just went through. And then we hook any events that are happening right now. We do have one more function of this that will draw a editor based grid for you to place initial objects on. You'll see what I mean when we get back into our editor once we finish reviewing this code. This section of code is going to be handling where we actually interact with our voxel container. So if we have a left mouse click, we're going to create a array based off the mouse position and the GUI. Then we're going to create a faux plane to intersect with, and that's going to be at our center position of the voxel container. So the center of that plane will be 0, 0, 0 within our octree, and then we run our array intersection code with that newly generated array. If item 1 is not null, which is going to be our ray intersect hit, but we hit on the plane via raycast. Then we want to go ahead and handle the interaction accordingly here. So this is going to be the easier of the two functions within here. We're going to get our hit point based off our ray. Then we're going to calculate our inverted voxel size, where 7 in this case, because we have a range of 0 to 7 based on our bit shifting, is going to be converted. And then we're going to divide our hit point divided by that 8 and then multiply it again to round out to our nearest 8th position or half position or quarter position, whatever. And we're going to modify the hit point based on the voxel container's transform position. So we're trying to convert our hit point into the local coordinates for that object. Then we're going to do a simple switch on the currently selected edit modes. If we're doing an add, we're going to call add based on all of the parameters provided within the toolbox window and our hit point. And then for remove, we'll just remove the voxel object. We don't care about the actual voxel here. And then we'll mark our voxel container and the serializable object as dirty and reinitialize the buffers to redraw it. Now, if we've actually intersected with something when we drew our ray, then we're going to just drop straight into a switch because it has to be handled differently when you're looking at the interior of an object for replace and remove, because in that case we care specifically about the node center. We don't care about the normal of the hit. So those are pretty straightforward. Replace is going to run add voxel, and that'll end up overriding the voxel at whatever position we're looking at here. Remove is of course just going to recursively find that position and remove it. Now normalized normal up here in add is going to be our hit normal from our ray march. We're going to again invert our voxel size here. In this case, we're going to be looking to get like 0.125 from our voxel size being 7 or our size of 1 in the case of a standard voxel. I think this normalize here might be redundant. It might be called during the ray intersection, but we're going to normalize the norm anyway. And then we're going to calculate a normalized point based off the node center minus the hit normal. As you can see by this commented out code, I was still working on getting the size working with the hit normals, but that'll soon enough. Then we get into the actual add voxel call, which is going to work just the same as it always does, using those parameters set within the toolbox itself. Just like with the plane, we set everything to dirty and reinitialize the buffers to save and redraw our object. Now the last function we're looking at here is the draw grid function. That's going to take in the half size of our root node and a, for the moment, grid spacing of 1, and then we'll define our origin based on the voxel container's transform position within the world. Then we're going to set our colors to gray and iterate through the grid size drawing lines between the end or the start and the end of each row. It's pretty straightforward here. So with all of that being said, we'll go ahead and save the editor here, and we'll drop back into our actual editor so you can see what we've actually done. And just like that, we have a floating window here with an add, remove, replace, our voxel ID of 0. You can see if we change that to 1, we automatically pick up the next color. Again, voxel size is currently inverted, so 0 is a full size cell. So if I were to click, you can see the hit normal detection is working even though we're not rendering, and you can add, remove. You can pretty much start creating whatever objects you want within this environment. You just won't have any nice rendering until the next part. But this was important to get a couple of the required structures set up, and in the next video I believe it will be almost entirely just going through the ray marching shader itself and getting that set up. So I know this one was a little bit boring for you guys, but I appreciate you checking it out nonetheless. And if you have any questions, as always, feel free to hop in the Discord and ask. If you like the videos, definitely like and subscribe. We're getting close to 500 subscribers right now, which is insane, especially considering I had like a 2-year hiatus. I appreciate all of you, and I hope you appreciate these tutorials. Thank you guys.